Dear students, in this video we will discuss about colloids. What are the points? Number 1, what is colloidal solution? Number 2, classification of colloidal solution. Number 3, preparation of colloidal solution. Two methods are there. One is condensation method, one is dispersion method. Number 4, purification of colloidal solution. Number 1 method is dialysis. Number 2, ultrafiltration. Number 5, properties of colloids. It consists of 3 properties. One is physical properties, one is mechanical properties, one is electrical properties. Mechanical properties includes Brownian movement and Tyndall Effect, and electrical properties includes coagulation, electrophoresis, Electro-Osmosis, zeta potential, and one theory is there, DLVO theory. And this coagulation is due to the presence of electrolyte, the behavior of the colloidal solution in presence of electrolyte, and electrophoresis and electro-osmosis are the behavior of the colloidal particles in presence of an electric field. Next is protective colloids, and number 8 is emulsions, and number 9 is micelle. So let's start. What is colloids? Depending upon the ability of the particles to pass through a vegetable or animal membrane, Thomas Graham classified the substance into 2 categories. One is crystalloid and one is colloids. So the crystalloids particles are very small and they can pass through the vegetable or animal membrane, and colloids particles are large compared to the crystalloids, which can easily pass through the vegetable or animal membrane. The substance which exhibit colloidal behavior, it depends on 2 conditions. One is the environmental conditions and one is particle size. Environmental conditions means the property of crystalloid or colloid may vary depending on the environment. For example, sodium chloride is crystalloid in water. They can easily pass through the animal or plant membrane. But sodium chloride behaves like colloid in benzene. Similarly, soap is colloidal in water, but it acts as crystalloid in alcohol. So depending upon the environmental condition, the property of the particles change. It may be crystalloid, it may be colloid. Next is particle size. To become a particle to colloid, the size of the particle is in between 10 to the power minus 9 meter to 10 to the power minus 7 meter. That means to behave a particle as colloid, it must have in between, the size of the particle must have in between 1 nanometer to 100 nanometer. If it is less than 1 nanometer, then it will be true solution and it is homogeneous. If it is greater than 100 nanometer, then it is suspension, it is heterogeneous. But if the size of the particle is in between 1 to 100 nanometer, then it is colloidal solution. Now, colloidal state consists of 2 phases. One is disperse phase and one is dispersion medium. As we already discussed that colloidal solution is a heterogeneous mixture. It consists of 2 phases. One is disperse phase and one is dispersion medium. Disperse phase is that phase where the particles are in small amount, and it is also known as inner phase. And dispersion medium is the particles are in large amounts and it is the outer phase, like solution where solid is mixed in a solvent. Similarly, disperse phase is mixed in dispersion medium. Depending upon the dispersion medium, the name of the colloidal solutions are different. If the dispersion medium is water, then colloidal solution is hydrosol. If dispersion medium is alcohol, then colloidal solution is alkosol. If dispersion medium is benzene, then the colloidal solution is benzosol. And if the dispersion medium is air, then the colloidal solution is aerosol. Sol means dispersed phase is solid and dispersion medium is solid, liquid or gas. Hence a sol defines as dispersed phase is solid and dispersion medium is solid, gas or liquid. Depending upon the dispersed phase and dispersion medium, colloids are classified, and there is one table, so you have to remember the name of the colloid depending upon the dispersed phase and dispersion medium and the examples. If the dispersed phase is gas and dispersion medium is liquid, then name of the colloid is foam. Examples: soft leather, whipped cream, soda water, etc. If the dispersed phase is gas, dispersion medium is solid, then it is solid foam. If dispersed phase is liquid, dispersion medium is gas, then it is liquid aerosol. Dispersed phase is liquid, dispersion medium is liquid, then it is called emulsion. Example: milk, cream, butter, etc. Dispersed phase is liquid, dispersion medium is solid, then it is gel. Curd, pudding, cheese. Dispersed phase is solid, dispersion medium is gas, then aerosol. And similarly, solid, liquid, solid, these are classified. You have to remember the name of this colloid with the examples. Next is, depending upon the interaction or affinity of the two phases, dispersed phase and dispersion medium, colloids are classified as lyophilic colloids and lyophobic colloids. Depending on the electric charge of the dispersed phase, colloids are classified as positive colloids, negative colloids. Depending on the molecular size of the dispersed phase, colloids are classified multimolecular colloids, macromolecular colloids, and associated colloids. Similarly, depending on the chemical composition, colloids are classified as organic colloids, inorganic colloids. First, depending on the interaction or affinity of the two phases, colloids are classified as lyophilic colloids and lyophobic colloids. Lyophilic colloids means the dispersed phase and dispersion medium have strong affinity for each other. They are also known as intrinsic colloids, and they are easy to form because they have strong affinity of each other, and it is not easily precipitated. So next stage of colloid solution is the precipitation, but it is not easily precipitated because of the high affinity for each other. Dispersed phase and dispersion medium have high affinity for each other. And examples are glue, gelatin, starch, protein, rubber, etc. While lyophobic colloids, there is no strong affinity between dispersed phase and dispersion medium. They are also known as extrinsic colloids, and they are stabilized by adding electrolytes. And the examples are AlOH3, FeOH3, AS2S3. These are the lyophobic colloids where dispersed phase and dispersion medium do not have any affinity for each other. Similarly, depending on the electric charge of the dispersed phase, colloids are classified as positive colloid and negative colloid. If the dispersed phase has positive charge, then it is positive colloid. Example: AlOH3, aluminum hydroxide in water, titanium oxide. And negative colloid means dispersed phase have negative charge, As2S3 in water, copper and gold salt. Similarly, depending on the molecular size of the dispersed phase, colloids are classified as multimolecular colloids, macromolecular colloids, and associated colloids. Multimolecular colloids means the dispersed particles are very small and they are aggregates They are combined by weak van der Waals forces, and they are lyophobic in nature. Examples: gold sol in water, sulfur sol. And macromolecular colloids are those where dispersed particles are large. For example, starch, cellulose, protein, polyethylene, polystyrene, etc. And associated colloids are those where the particles shows normal electrolytic behavior at low concentration, but at high concentration they aggregate and shows the behavior of colloidal particles. So colloids are classified according to the source, and they are multimolecular colloids, macromolecular colloids, and associated colloids. Next is how colloids are prepared. Colloids are prepared by basically the lyophobic colloids are prepared by two methods. One is condensation method and one is dispersion method. Condensation method is classified in two types. One is physical method and one is chemical method. And in condensation method, what are the physical methods? One is solvent exchange, another one is excessive cooling, another is condensation of hot vapor under liquid phase, and next one is controlled condensation. Solvent excess method is applied for the colloidal solution of phosphorus and sulfur. For the preparation of colloidal solution of phosphorus and sulfur. Here the particles are first dissolved in a solvent where it is soluble, then it is poured in a solvent where it is less soluble or insoluble. So colloidal solution of sulfur and phosphorus can be prepared by first dissolving them in alcohol where they are soluble, and then it is poured in excess of water where it is not soluble, and alcohol can be removed. Next is excessive cooling. So by this method, colloidal solution of ice can be prepared by freezing a mixture of water and organic solvent such as chloroform or pentane or ether. Next is condensation of hot vapor under liquid phase. By this process, salt of mercury and sulfur can be prepared. How they are prepared? Salt of mercury and sulfur by passing the vapors of mercury and sulfur through the cold water containing a suitable stabilizer. Next is control condensation. By this method, control condensation, salt of Prussian blue can be obtained. So the colloid solutions are prepared by precipitating them in the presence of some colloids like starch gelatin. By this method, salt of Prussian blue can be obtained. Next is chemical method. So chemical method include oxidation, reduction, hydrolysis. The oxidation method is applied for the preparation of salt of non-metal. For example, when H2 gas is passed through the bromine water, then sulfur salt is obtained. Similarly, H2 gas is passed through the sulfur dioxide, then sulfur salt is obtained. Similarly, reduction method is applied for the preparation of salt of metal. Gold salt can be obtained by the reduction of gold AuCl3 with SnCl2. So this is reduction method. Next is hydrolysis method. So colloidal solution of many oxide can be prepared by this method. When concentrated solution of FeCl3 is poured drop by drop in hot water, then we will get ferric hydroxide salt. Similarly, ferric acetate is when treated with hot water, then ferric hydroxide salt is obtained. In this process, acetic acid is removed immediately so that we can get the FeOH3 salt effectively. Next is double decomposition. In this method, the salt is prepared by combining with two insoluble salt. For example, very dilute FeCl3 is treated with K4FeCN6, then Fe4FeCN6 is obtained. This is a sol. Similarly, this arsenous oxide is means H2S gases pass through arsenous oxide, then we will get AS2O, AS2S3 salt. Next is dispersion method or disintegration method. Dispersion method or disintegration method means breaking of the particles. So first one is mechanical dispersion, that is breaking by mechanical way, and second is electric dispersion of Bradick's arc method. So one method is there, that is Bradick's arc method. In this process, two metal electrodes are connected in an arc, and it is immersed in a dispersion medium like water. This water consists of potassium hydroxide, which is used to stabilize the salt, and the solution is kept cool by keeping it in a bath, cool bath. Now the local heat emerged from the arc will vaporize the metal rod, and the metal obtained will be passed to the dispersion medium, that is water, and this immediately that metal vapor will be condensed in water, and this will get that metal sol, and this sol is stabilized by potassium hydroxide, and this method is known as Bradick's arc method. Third one is peptidization. In this method, the freshly prepared ionic solids can be prepared to colloidal solutions by adding small amount of electrolyte. The added electrolyte and the ionic solid has one ion in common, so that common ion will repel with each other. For example, we have a ferric hydroxide precipitation, then we are adding some Fe3 positive ion from outside as a electrolyte. Suppose FeCl3 is added, then we will get a sol FeOH3 Fe3 positive. How it is obtained? In addition of Fe3 positive from outside in a FeOH3 ions, since Fe3 positive is common in FeOH3 and FeCl3, so the positive ion will repel with each other. So the positive particles of FeOH3 repel with each other, and hence they will not able to come close to each other. As a result, the colloidal particles will form. Similarly, if silver ion as an electrolyte is added in a silver chloride precipitate, then a silver salt will be obtained. Similarly, here common ion is silver positive, so the positive ions will repel with each other, and they cannot come close to each other. Next is purification of colloidal solution. So two methods are there to purify colloidal solution. One is dialysis and one is ultrafiltration. So dialysis is the method where the colloidal particles are passed through a dialyzing membrane, that is maybe animal membrane or plant membrane, and this method is used to separate colloidal particles from soluble impurities. And animal membrane and parchment paper is used, which is very fine pores, and due to these fine pores, the pores permits the electrolytes which have small size, but they do not allow to pass the colloidal particles through the membrane to the outside. Now, if an electric field is applied here, this is the diagram where this is a dialyzing membrane, and here inside the impure colloidal substance are there. If the electric fields are applied, here positive, here negative, that is anode, that is cathode. Now depending upon the electric field, the electrolytes, the crystalloids which are impure crystalloids will pass to the solution outside the membrane according to the positive or negative charge of the electrode. So negative crystalloid will pass towards the anode and the positive crystalloids pass towards the cathode. So this is known as electric dialysis, and according to this method, the colloidal particles which have soluble impurity we can prepare. Next is ultrafiltration, and this ultrafiltration means in this method we will use an ultrafilter paper similar like this. We will use an ultrafilter paper to separate the salt particles from the liquid medium, and the ions and the molecules of impurities pass through these pores of the ultrafilter, but colloidal particles will retain in the solution. Next is the properties of colloids. So this includes physical properties, mechanical properties, and electrical properties. So physical properties means first one is they are heterogeneous in nature. Colloidal particles are heterogeneous in nature. They are quite stable. And next is they cannot be separated by ordinary filter paper but through enamel membrane or parchment paper. Next is they are not visible to naked eye or under ordinary microscope. And they observe the colligative property, only one colligative property they observe, that is osmotic pressure determination. So colligative property, osmotic pressure. So osmotic pressure of the colloids can be determined. Next is mechanical properties. So mechanical properties means number one is Brownian movement. So if we observe the colloidal particles in a microscope, ultra microscope, not in an ordinary microscope, in an ultra microscope, then we will see that the colloidal particles will continuously moving in a zigzag pathway. It's a zigzag pathway, and this movement is first observed by Robert Brown in 1827. That's why the movement is known as Brownian movement. Why the particles is observing Brownian movement? Because the molecules in dispersion medium, due to their kinetic motion, strike against the colloidal particles. So the dispersion medium's molecules is moving, continuously moving, and they are striking against the colloidal particles from all sides, from many sides, from different sides, with different forces. Different forces are there. So they are moved in a zigzag pathway. That is Brownian movement. And the second property is, before going to second property, another thing is that comparatively heavy particles move with the slower speed. Heavy particles will move in a slower speed. And what is the importance of Brownian movement? Number one, that Brownian movement opposes the force of gravity and does not allow the colloidal particles to settle down. So Brownian movement is very important for the stability of the colloidal solution. And second thing, it helps in determination of Avogadro number. So I'm not discussing the determination of Avogadro numbers here, but Brownian movement helps in determining the Avogadro number of the particles. Next property of the colloid is optical property, that is Tyndall effect. And Tyndall effect is first observed by Tyndall in 1869, hence the name is Tyndall effect. And this effect is the scattering of light by the colloidal particles present in the colloidal sol. So when a strong beam of light is passed through a colloidal solution, and if we observed through a microscope perpendicular to the path of the light, then we will see the illumination of blue light. This is because the colloidal particles are scattered due to the light present, and hence we are seeing the blue illumination. And this is similar like suppose there is a wall and a hole is present inside the wall, a hole is present, and we are allowing to pass the sunlight through the hole, and we will see the part of the light. In the part of the light we will see some dust particles. This dust particle is scattering the light, that's why we are seeing the part of the light. So similar is the case in the colloidal particles. We will see the blue illumination due to the scattering of the light. The illuminated part is known as the Tyndall cone. Two conditions must be fulfilled to show the Tyndall effect. First is the difference of the refractive index of the dispersed phase and the dispersion medium must be comparable, and next is the diameter of the colloidal particle should be comparable with the wavelength of the light. So these two conditions must fulfill to show the Tyndall effect. And based on this Tyndall effect, Zygmunt, one scientist, devised ultramicroscope which gives the information of size and shape of the colloidal particles. And Tyndall effect is also useful to prove the heterogeneous nature of the colloidal solution. So Tyndall effect have two applications. One is the design of ultramicroscope, and second is to prove the heterogeneous nature of the colloidal solution. Next is electric properties of the lyophobic salt. The electric properties of the lyophobic salt can be studied by two conditions. One is when an electrolyte is added to the salt, what will happen, and second is when electric field is applied, what will happen. If a small amount of electrolyte is added to the colloid, then the colloid is stable. But if a large amount of electrolyte is added to the colloid, then the particles is precipitated out and it leaves a clear solution, and it is known as flocculation or the coagulation. Why the coagulation is happen? The coagulation is observed due to the presence of charge particle, due to the presence of charge in the colloidal particles. The origin of the charge is explained by the preferential adsorption of the ions. Preferential adsorption of the ions by the colloidal particles. According to this, the colloidal particles absorb positive or negative ions on their surface preferentially and hence acquire a positive or negative charge. So the colloidal particles are charged due to the preferential adsorption of positive or negative ion. So on addition of excess of electrolyte, the oppositely charged electrolyte neutralize the charge of the colloidal particle. Suppose this is one colloidal particle, addition of electrolyte, the oppositely charged ions is neutralize the colloidal particles and result in the precipitation of the ions. Now, Schulz, Hardy, Linear and Picton formulated two rules, and according to this rule, ions carrying the charge opposite to that of the colloid particles are affecting in inducing coagulation. So for coagulation, the added electrolyte must have negative charge compared to the colloidal charge. And second rule is the larger the valency of the coagulating ion, the greater will be the coagulating power. So the larger the valency, the greater will be the coagulating power. For example, AS2S3 is a negative sol, so the coagulating power will be explained in positive electrolytes. And the electrolyte which coagulating power of the electrolytes has the order 3 positive is greater than 2 positive than 1 positive. And similarly, to precipitate FeOH3 sol, a positive sol, the coagulating power of different anions, which is, since it is a positive, so the negative charge is there, and FeCN6 4 negative is greater than FeO4 negative, SO4 negative, then Cl negative. So charge is opposite, and greater the charge of the ion electrolyte, more coagulating power. Next is effect of applied electric field on lyophobic sol. So when an electric field is applied in a lyophobic sol, then two phenomena are observed. One is electrophoresis and one is electro-osmosis. So this is the diagrammatic representation of electrophoresis, and this is the diagrammatic representation of electro-osmosis, that is endo-osmosis. So what is electrophoresis? The existence of charge in the colloidal particles can be explained by electrophoresis. So electrophoresis means the particles, the movement of colloidal particles towards the positive or negative electrode when placed under the influence of an electric field. So when the colloidal particles are placed in an electric field, then the colloidal particles will move to the oppositely charged electrodes, that is cathode and anode, and the negative ions will move to the anode and positive part will move to the cathode. This is electrophoresis. The movement of the colloidal particles under the influence of the electric field is electrophoresis. Similarly, electro-osmosis is there, that when a membrane is present within the colloidal particles, and in presence of an electric field, the molecules of the dispersion medium are allowed to move under the influence of the electric field, and the colloidal particles are not allowed to move. The colloidal particles are not allowed to move, but the dispersion mediums are allowed to move through a membrane, and the negative charge will move to the positive electrode, and the positive charge will move to the negative electrode, and this is called electro-osmosis. Next is zeta potential or DL-VO theorem. Now, in colloids, at the interfaces of the two phases, so at the interfaces, colloids have two phases, one is dispersed phase and one is dispersion medium. So the interfaces of the two phases, the preferential absorption of the ion of the surface of the dispersed phase, suppose this is the solid dispersed phase and this is the dispersion medium, then the preferential absorption of the ion in the dispersed phase results the counter ion will absorb in the dispersion medium next to the dispersed phase. So suppose dispersed phase is the I1 and I2 is the dispersion medium, which is a fixed part, and I3 is the solution in bulk. So the preferential absorption of the positive ion in the dispersed phase results preferential absorption of the counter ion in the dispersion medium results a double layer, and this layer is known as electrical double layer, and the potential difference between the solid surface and the fixed part of the counter ion is known as the double layer potential, that is psi. And the potential difference between the I2 and I3, the fixed part of the counter ion, and the solution in the bulk is known as the zeta potential. And the potential difference between I1 and I2, that is called the double layer potential, and difference between I2 and I3 is known as zeta potential, and it is expressed by Chi. So this is the electrical double layer. Electrical double layer observed when the interface of the two phases, the preferential absorption of the one ion results the preferential absorption of the counter ion in the interface of the colloidal particles, and this results a electrical double layer. And the potential drop of this double layer, it may drop or it may again rise. The potential drop of the double layer can be explained by DLVO theory. DLVO theory means Darza-Quinn, London, Varley and Overbeek theory. And this potential drop is because of the attractive and repulsive forces between the ions. So the diffuse double layer of the colloid particles interact when particles approach each other, and the interaction energy depends on interparticle distance and the reciprocal of the thickness of the ion of the atmosphere. So the interaction energy of these two ions depends on the interparticle distance, the distance between the particles, and the reciprocal of the thickness of the ion atmosphere. And second is the interaction energy is repulsive and result repulsive potential energy curve. Already we have seen that the interaction energy is repulsive and hence it is the repulsive potential energy curve. But the interaction energy is further explained by London, that it is the van der Waals forces that operates between colloidal units which is attractive. So the potential energy curve is due to the attractive forces and the repulsive forces of the colloidal particles. At short and long distance, the attractive forces predominates, and the intermediate distance between the particles repulsive forces predominates. So at short and long distance the attractive forces predominates, and the intermediate distance the repulsive forces predominates. Now addition of electrolyte affect the repulsive potential only. So addition of electrolyte affect the repulsive potential only, and hence decreasing the thickness of the ion atmosphere. So decreasing the thickness of the ion atmosphere. So ion atmosphere has the thickness is less, then the repulsion potential become prominent. So the repulsion potential become prominent, and this explains the colloidal stability and coagulation. This is the DLVO theory. Next is protective colloid. Now, as we know that the addition of small amount of electrolyte brings the precipitation of lyophobic sol. So when a lyophilic colloid is added to the lyophobic sol, then the stability is enhanced. Now already we know that the addition of small amount of electrolyte brings the precipitation of the lyophobic colloid. Now if a lyophilic colloid is added to that lyophobic colloid, then the precipitation can be stopped. And these lyophilic colloid added are gelatin, gum arabic, agar-agar, etc. So the lyophilic colloid added for the protection of lyophobic colloid. To protect the lyophobic colloid from precipitation, the lyophilic colloid is added, and this is known as protective colloid. So the lyophilic colloid which is added to protect the lyophobic colloid from precipitation is known as protective colloid. To express the protecting power of the lyophilic colloid, the term gold number is used. The term gold number is used to express the protecting power of the lyophilic colloid. It is defined as the number of milligram of the protective colloid, that is the lyophilic colloid, required to just prevent the precipitation. So it is the number, gold number, the number of milligram, the number is in milligram of the protective colloid, that is the lyophilic colloid, required. How much milligram of the lyophilic colloid required to just prevent the precipitation, to prevent the precipitation of 10 ml of given salt, 10 ml of the given salt, when 1 ml of the 10% solution of sodium chloride added to it. Suppose there is a lyophobic colloid which is in 10 ml. Suppose we have 10 ml of lyophobic colloid where 1 ml of 20% solution of sodium chloride is added. This is electrolyte is added from outside. So it will precipitate. Now to protect this precipitate, how much milligram of lyophilic colloid required? This is the gold number. So gold number, larger the gold number, the less will be the protective power. The smaller the gold number, the protecting power will be more. So these are some gold numbers of protective colloids. Gelatin has 0.005 to 0.01, stars 15 to 25, gum arabic 0.15 to 0.25, egg albumin 0.1 to 0.2, hemoglobin 0.03 to 0.07. So smaller the value of the gold number, that means the amount required is less. So the gelatin has the greater protecting power. Next is emulsion. So emulsion is also a colloidal mixture where the dispersed phase and the dispersion medium both are liquid. There are two types of emulsion. One is oil in water, the example is milk, and one is water in oil, the example is butter or cream. Now the substance that is added to stabilize the emulsion. So oil in water, it is not stable, or water in oil, it is not stable. So sometimes the substance is added to stabilize the emulsion, and that is called emulsifier or emulsifying agent. For example, sodium or potassium salt of higher fatty acid, sodium palmitate, sodium stearate, C15H31. This is a higher, longer chain. C17H35. This is a longer chain. So, longer chain of higher fatty acid. It's a sodium salt of higher fatty acid. It is the emulsifier. This is the structure of a longer fatty acid. This is the polar group, it is head, and this is the longer chain is non-polar group, this is tail. Now what will happen? Suppose this is water, there is a one oil droplet, that is oil in water, suppose emulsion, oil in water emulsion. How it will stabilize? The non-polar part will headed towards the oil and polar part will be directing towards the water. Hence, it will form a spherical aggregation. This is known as micelle. We will discuss in the next part. So, during the formation of oil in water emulsion or water in oil emulsion, the emulsifier arrange themselves in such a way that the non-polar groups directed towards oil and polar groups directed towards water. Hence, it is stabilized. And as a result, the interfacial tension between water and oil decreases and they are intermixed. Next is micelle. Micelle is actually an associated colloid. Already we have discussed that associated colloid which behaves in low concentration as an electrolyte, but in high concentration they behave as colloidal particles. Micelles are associated colloids which behaves as electrolyte in low concentration and behaves as colloids in high concentration. Soaps and detergents are the common examples of micelles. Already we know these are emulsifier, sodium stearate, sodium palmitate, which have longer chain of fatty acid, and this is the sodium salt of longer chain of fatty acid. This is sodium salt of longer chain of fatty acid. So the concentration above which the micelle formation start is termed as critical micelle concentration. So the concentration below which it behaves as electrolyte, and the concentration above which it behaves as colloids, it is the concentration as critical micelle concentration. Now the mechanism of micelle formation, cleansing action of soap. How soap cleans the dirt? Suppose this is a cloth, this is the dirt. This dirt means this is suppose grease. It's a non-polar substance. Now if we added a soap solution here, then the soap solution means it will form a micelle, where the soap solution means the longer chain of fatty acid which have a polar group and a non-polar group. It's a tail and it's a head. Now the non-polar group will directed towards the oil particle, and polar group will directed towards the water. Now it will form a circular aggregation, that is micelle, and as a result of this micelle formation, the dirt particles will come out from the cloth and it will clean the cloth. This is the formation of micelle. The water is there. This polar head is directed towards water, and non-polar tail is headed towards the oil particle. This is hydrophobic part and this is hydrophilic part. So that's all for today. These are the topics related to colloids. Thank you.